All right, so like I said, we're going to do the logistic model now. So what I'm going to do is I'm going to first rewrite this as 16 times 1 plus 2.1 e to the 3.9 t to the negative 1. Now, I have a number times this. So I'm going to know with the logistic, we have inside, we have the next inside, and then we have the whole thing. So what I'm going to say is let's take and do g of t is equal to, and that'll be 3.9t. Okay. And then f of g we can say is 1 point, or not 1 plus 2.1 e to the 3.9 t. Okay. Not 3.29 t. Well, that's just going to be a G. Okay. Got to remember we took that out and we put that here. And then maybe we could say L of F was equal to, now it's going to be 16 times F to the negative 1. So we replace that with F. And those three, we can easily find the derivative. And so G prime of T is equal to what? Well, it's 3.9. F prime of G, well, that's just 2.1 e to the G. And L prime of F is minus 16 F to the negative 2. Okay. So how do we find L prime of T? We just multiply all those together. So we'll have 3.9 times 2.1 e to the 3.9 t times negative 16 times, and then we have 1 plus 2.1 e to the 3.9 t, and then it's going to be to the negative 2. Okay, now I'm going to leave it with the negative 2 here, but because now I have to take the second derivative, I'm going to go ahead and multiply this times this, and that's going to help me hopefully with my second derivative. And so if I plug all that in, I'll have, uh, let's see, 3.9 times 2.1 times negative 16. So I get negative 131.04 e to the 3.9t times 1 plus 2.1 e to the 3.9t to the negative 2. All right, so now I've got this for my first derivative. Now I need to take the derivative of this. This is where it starts getting a little more complicated. So now I'm going to have a product. I'm going to have that times that. So let's call that g of x, and let's call that h of x. And so what I can do then is say, well, g of x is equal to a negative 131.04 e to the 3.9t, and h of x is equal to, and then we have 1 plus 2.1 e to the 3.9 t to the negative 2. Okay. Well, with g, I can find that derivative. So that's just going to be the number, negative 131.04 times, well, now I'm going to take the ln of this, but that's going to be 3.9 can come down front, then the ln of e is 1, so then it's just times 3.9, and then it's times e to the 3.9t. Now, once again, I'm going to multiply those together, and so I'll have a negative 131.04 times 3.9, and so that gives me g prime of x equals a negative 511.056, and then that's e to the 3.9t. All right. Now, what I have to do is I have to do this piece. And so I'm going to break that down like I broke it down here. And so now I'm going to kind of maybe give me extra space. Maybe I can get it all on this page. And so now I'm going to say, okay, well, let's do g of t again. And so that's going to be my 3.9t. And so we have 3.9t. My f of g is equal to, now it's going to be 1 plus 2.1 e to the g. And I don't know, let's do h of f because I want to get to h derivative. So we're going to go ahead and call it h of f. And that's going to be, and now we have, it's going to be f to the negative 2. Okay. Well, g prime of t is 3.9. F prime of g is 2.1 e to the g, and h prime of f is equal to negative 2 f to the negative 3. So then h prime of x, which is what we're looking for here, is equal to, well, now we just multiply 3.9 times 2.1 e, and that's to the 3.9t. And then that's times the negative 2, and then that's times our 1 plus 2.1 e to the 3.9t, and it's to the negative 3. Now again, 3.9 times that, I'm going to do that to simplify it. So I'll take 3.9 times 2.1 times negative 2, and I get a negative, let's see, 16.38 it looks like. And then that's going to be e to the 3.9t times 1 plus 2.1 e to the 3.9t to the negative 3. Okay, so that's what my h prime of x is equal to. So now this is really going to be kind of down here, and now I'm going to take my g prime, this, times this, plus this, times this. So now for the next page, then I want to go ahead and get that all figured out. So I'm going to have, now what did I have there? Negative 511.05. Whoa, I didn't give myself enough room on this one. So we'll do it here, I guess. And so then the L double prime of t is equal to, now I'm going to have negative 511.056 e to the 3.9t, and times this, which then I'm going to put over to make it so we have less room, 1 plus 2.1 e to the 3.9t squared, plus, now I have this times this, so I only want to write it once. I'm going to take that 16.38 negative times, and it was times a negative 131.04. So that's 2146.4352. And then I have this piece times this piece, okay? And if you think about that, e to the 3.9t times e to the 3.9t, well, we're just going to add those together, and we're going to get e to the 7.8t. So then we'll have e to the 7.8t. And then we have, let's see, where are we at here? So that was my g. So now I've got that. So now all I have left is over 1 plus 2.1 e to the 3.9t cubed, okay? And so that then is my L double prime. This was my L prime, so my second derivative, my first derivative, and my original function, okay? So like I said, that one takes a little bit more work because, we have that logistic, and logistics are always harder. But then, getting to the first one, that's not hard. It's the second one where you have to keep track of everything along the way to make sure you get down to that final one. And of course, a lot of the application problems for this section are of the type here, logistics. So we're going to have a couple of those we're going to work on today. All right, so now what we want to do is we want to write the first and second derivatives of the function and use the second derivative to determine inputs at which inflection points might exist. All right, well, let's first find f prime of x and f double prime of x, the first and second derivatives. So that's 3x 3x squared, sorry, 3x squared minus 12x plus 12. That becomes 6x minus 12. And so now I'm going to say, okay, well, let's set that equal to 0. And so now 6x is equal to 12, so x is equal to 2. And so that's going to be my input for the possible inflection point, okay? that might exist. And so that's going to be where I plug it in. And I'll plug that back into my original function too. And if I go to my graph, it should be the inflection point. What about this one? Okay, well, we're going to do the same thing. We're going to find our two derivatives, first and second derivative. So this is going to be 98 times, well, again, this is going to be ln of 1.2 times 1.2 to the x plus 120 times ln of 0.2 and then times 0.2 to the x. Now, when we take the second derivative, again, that's a number, so we're just going to take 98 times ln 1.2. Then we take the ln of that. Well, we already have one of those, so now let's make it 2. We've seen that already, so that's not going to be a surprise. And then times 1.2 to the x. Plus, now we have 120 ln of 0.2, and again, that's going to be squared times 0.2 to the x. All right, so now we have to remember that, and we're going to go solve that in our calculator. Okay, so we're going to do math, numeric solver, enter, and we're going to put in our function there. We just found the derivative, and so that was not. Did I write it down wrong? Yes, this is supposed to be 9.8, I believe, and 120. Let me check the book here real quick. I think I have a typo here on one of them. It's either my copy or what's online here. It is just 98. Okay, so we'll do 98. That's not a problem. And so I just have to remember my copy is wrong. Okay, so 98, and then we had the ln of 1.2. And let's put it actually in parentheses like this so I know I'm squaring that whole thing. Okay, so I want to square that whole thing. And that's squared. And then times 1.2 to the x. And oops, arrow down and then parenthesis. So that looks good for the first part. And then I'm going to say plus 120 and then times the ln of 0.02 or 0.2, sorry, 0.2, and then in parentheses square that one, and then times 0.2 to the x, arrow down. Arrow down and have that. Now we can do this. And so let's type it in here. Aha, no sign change. Okay, so this is one where it's going to say, hey, there's no inflection points. And so that's what you'll see is if there's no sign change on your second derivative, then we say no inflection point exists. And, on a calculator says no sign change. Okay, so that's how we figured out that one because it gave us no sign change, so that means no inflection point actually exists. All right, so let's stop there and we'll come back for more.